My name's Tom Davis, and I'm going to be talking about a topic called Conway Tangles, and it just has to do with how to use mathematics, how to apply mathematics to some tangled up ropes. And what I like about it, about the subject, is that there are a couple things I like about it. One is that you can use it for classes at almost any level. Basically, all you need to do, all the kids need to be able to do, is to be able to do arithmetic with fractions. The nice thing about it also is that, and it can be almost as advanced as you want. You can keep going and going and going and find more and more advanced topics. So there's no upper limit either. The other nice thing I like about it is, in order to sort of solve the problems that we're going to be solving, you actually have to do a bunch of arithmetic with fractions. And so, although the kids think they're solving the problem, you're actually drilling their fraction arithmetic, which is never a bad thing. So, here's how it works. I need 4 volunteers. Need 4 volunteers up here. And I need 2 of you facing 2 of them. So this will be the standard position. Hang on to that. Your main goal is to not let go of your end of the rope. Yeah, in fact, with kids, a lot of times, you'll find one of them starting to jerk the rope, and they'll pull it out of the other one's hand, and then it's a disaster because it's really hard to keep track of exactly where it was. You can never undo. I mean, as you'll see, if you get mixed up, it would be very, very bad. So what I often tell the kids to do is, wrap it once around like that or something like that. From the mathematical point of view, the 2 ropes are identical. They're supposed to be the same color, indistinguishable, and the people are indistinguishable too. So you're all identical in some sense. All that we care about mathematically is what we're going to do. It's sort of like a square dance, where I'll have a couple of figures that you do, and as you shift around, obviously the ropes are going to start getting tangled up with each other. And all that we care about mathematically is the tangle in the ropes that exist. And so if we have exactly the same tangle, but 2 people are in different places, that's the same thing. Or if the ropes are in different, if it's the yellow rope or the green rope, that's the same thing. The reason I have 2 colored ropes is for the audience. When we have a tangle and I want to display it to the audience, it's much, much easier to sort of see how the ropes tangle around each other if you've got different colors. It's also a good idea if you're doing this to get ropes, the thicker the better in some sense, because if you've got real thin ropes, you can get a little knot that's very hard to undo. I mean, in fact, some of the things we do today will seem maybe a little hard for that. So the whole idea is, we're going to start with the 2 ropes in, this is like the 0 position, where the 2 ropes are parallel to the front of the class, like this, held like this. And each time we do a dance figure, we're going to modify the number. So we're going to say, this is 0, and when we do things to it, it changes that 0 to other things. And the amazing thing is the numbering scheme is going to keep track in some weird way of the condition of the tangle. So let me just start off with the simplest figure. And since you're going to be shifting around like in a square dance, everybody has to pay attention to what's going on, because when I say you do this and you do this, you may be in this position. Okay, so the first figure only involves these 2 people, or the 2 people that happen to be standing here. And it's called twist. And it's very simple. The person behind here, Consuelo, you lift your hand, you step under, and then you step into her position. And that's it. So that's figure 1 is called twist. And what we're going to do, and I'll just say this at the start, is twist takes whatever number you had before and adds 1 to it. So this would represent 1, because we started at 0. The parallel ropes always represent 0. We've done 1 twist, so this is 1. Let's do another twist. And now we have 2. Let's do 1 more twist. In fact, let's do 2 more twists. That's 1, that's 3, and that's 4. Okay, now for the third figure, which is the most important, and that is for the benefit of the class, you want to display the knot. So the command is display. The two people in front sort of hold your end down, and the two people in back hold it up. And now the tangle here is displayed to the class, and the class has to. So this is a 4 that's being displayed, right? You can sort of see this is a pretty simple idea. If twist were the only command, the only moving command, it would, I mean, we could do it for a while, but you can sort of see what's happening. We're going to twist it tighter and tighter and tighter. And each time you add 1 to the knot, it basically is an additional half twist in some sense. So if we're at 7, it's like 3 1/2 complete twist is what a 7 would represent. Now, unfortunately, we don't have the untwist command, which would be the obvious thing. You just reverse what you did here. But let's just, and again, this is a good thing for a class to sort of give the idea of what I mean by associating numbers with the tangles. Is suppose that the dance consisted only of twist and untwist commands. You did, if that were a legal thing to do, then it would be pretty clear what would the untwist command do to your number. It would subtract 1, right? So if you suppose we do this twist-untwist dance, this moronic dance for a while, and magically we come up and I do a display and it's 4. What can we say about what happened? Exactly. So the number of twists minus the number of untwists was 4, and you have no idea. It could have been 1,000,000 twists and 1,000,000 minus 4 untwists. But all you can say for sure, and in any order, all you know is that the grand total of twists was 4 more than the grand total of untwists. And obviously, untwists could take you into negative values, and that's fine too. I mean, if you were at -3, that would simply mean 3 twists would get you back to 0, right? But as I say, untwist is not a valid command. So, the only other dance figure is the second figure, and that's called rotate. And what we do here is everybody takes 1 step around clockwise from somebody looking down in the ceiling. Okay, so you move to this position and so forth. So that's just 1/4 turn. So there's the rotate command. And display. And you can see sort of what happens. It's going to take whatever kind of a tangle you had and turn it 90 degrees. Let's do another rotate. And what's the situation now? Any guesses about what number we got with 2 rotates? We started with 4. It's still got the same number of turns, right? The question is, did they reverse direction or not, right? I mean, a good guess would be it's either 4 or negative. I mean, without even thinking about it, it's probably 4 or -4, right?
Negative 4.
And how could you test whether you've got -4 or not?
Do 1 more twist.
Do 4 more twists, right? I mean, then it would, if it's truly -4, then 4 twists should bring us to 0. I think you can sort of take a look and, well, let's do 1 more twist. It's going to get worse, right? It's going to actually probably take it to 8. So, in fact, the 2 twists did what? I mean, the 2 rotates. The 2
cancel each other out.
They basically canceled each other out. I think it's totally obvious. Well, if you think about it, each of you sort of sees the ropes twisting away from you in a clockwise, in the same direction. And just if you turn around to the other side, they're still going to be twisting away from you in the same direction. So if all we had were twist commands, then 2 rotates in a row is just going to turn it back. And since the colors of the rope don't matter, and since the positions of the people don't matter, the 2 rotates will basically leave the situation exactly the same. Yeah?
So when the 1 rotate, besides changing the position of the rope, does it change the value?
Yes. And the question is, what does it change it to? Now, for an elementary class, for kids that don't, you can just tell them the answer. And I'm not going to tell you, because it's actually sort of an interesting problem to try and figure out what, if twist adds 1 each time, what should I say rotate does? To fit mathematically into into the equation, okay? So I'm going to do another thing that's illegal according to the standard rules of the dance, and that's I'm going to push the reset button rather than trying to untangle it. So why don't you just, I want to get back to 0 basically without going through some twisty dance thing. Yeah?
Is the twist always done by the
Always.
back pair?
The pair on one side, and it's always the person in the back holding the hand up, the person in front
Okay,
on
it's
this
always
side
on that
stepping
side.
under. Yes, and it turns out it doesn't matter, but it's good to you can pick any side. Just always, as long as it's the same, it'll work out.
And
So
it's always
I've
the
always
back.
done it this way, so I don't get confused.
Okay.
Okay. So here we are at 0. And if we wanted to figure out what the rotate command does, a reasonable thing to do would be to sort of investigate what rotate does to some small numbers. And a good small number might be 1. So we're at 0 now, do a single twist, that'll put us at 1. Okay, so let's try and figure out what does a rotate do to the number 1. Let's do a rotate. Okay. Now it still looks like a sort of a half twist. I guess you could do a display here in case we're
The back.
yeah, it sort of looks backwards, right? So this looks like a 1 or a minus 1, but which one is it?
One, and you twist it, you get back to 0.
So let's do a
Yeah.
twist. Ah. So the rotate apparently takes 1 to minus 1. Right? Let's just do it again to make sure everybody's got it. We're at 0 here. I do a twist. That twist always adds 1. So we're now clearly at 1. We do a rotate. We're now at some unknown number. But if I take this unknown number and I twist it, I'm to 0. And I had to add 1 to get to 0, so the unknown number must have been negative 1, right? So in other words, we do now have a fact, namely that rotate takes the particular number 1 to negative 1. So any guesses about what rotate does? Yeah. Okay. So how can we test that today? Try 2. Okay. So we're at 0. Twist, twist. Now we're at 1. Now we're at 2. Now do a rotate. So in theory, if your theory is correct, we are now at negative 2. Okay, so how would we test that? Two twists. 1, 2. So that's not quite right.
Okay, so I'll rotate
What does it look like now?
Yeah, okay, yeah, display.
Oh.
Nothing we know?
Oddball. Okay, let's do a reset here.
Yes, step.
Actually, if we were just to reset to undo what we just did,
Yeah.
could we do 1 rotate and then twist, twist? Oh, 1 rotate.
No, right, 2 untwists.
Yeah.
Yeah. Or 2 untwists and a rotate. If we didn't get twisted. Yeah. This is another interesting thing. This points out, and we'll see this comes up over and over again. It's just a general mathematical idea that if you have this some kind of a mathematical operation that does, let's say a series of operations, you know, A does one thing and then B does something else and C does something else. If you do A, then B, then C to something, if you want to undo it, you undo C, then you undo B, then you know, it's when you invert, it's not just in any arbitrary order. You better undo them. You know, you put your socks on, then your shoes. If you're taking them off, you can't take your socks off first. You got to take the shoes off first. You got to undo the shoe putting on before you undo the sock putting on, right? Yeah.
But in terms of the learning process, when you're doing this with the class, do you find it better, like, when they get to an unsuspected position, they make an error, you don't say reset, you actually make them do a rotate
No,
and
I-
twist to back up one step
When I'm
at a
just
time.
trying to get started,
Right.
I think it's faster rather than just going through, you know, just
Okay.
mechanically trying to untangle it. We'll get to the place where there'll be a lot of action pretty soon. Okay? So, but I wanted to point out, and as I say, in a lot of classes, you could just tell them, this is what the rotate command does, and then we could start into some actual interesting tangles. But what I wanted to do here, since we're more advanced maybe, is to actually show ways you might lead to, you know, how, I mean, in real mathematics, you say, well, what in the heck is going on numerically here, or even is there a numerical thing that's going on? And you make conjectures, you say, well, it's turned 1 to -1, so maybe it just flips the sign, and then, well, how would you test that? We'll try it with 2, and no, that's not working, okay. But here's an interesting thing. When we did a whole bunch of twists, it sort of made a spiral that was, you know, clockwise, at least from some point of view. And if we had been allowed to do untwists, in other words, the negative of that operation, it would have generated a spiral, but sort of a mirror image of it, right? Twisting in the opposite, a spiral going in the opposite direction. So in some sense, you know, a theory that, again, I don't have any proof for this, but a reasonable thing is the negative of a number is somehow just the mirror image of the knot, you know, the tangle. Is a reason. Does that sort of make sense? Because the mirror image of a spiral going clockwise would be a spiral going counterclockwise. And if you have a counterclockwise spinning spiral, then clockwise spins will undo it. So that, you know, if you had a +3, then you'd need -3 to undo it. But if you had a -3, then +3 would undo it. So it's sort of the mirror image. So here's an interesting thing. Let's do the. We're trying to figure out what rotate does to the number 2. We know what rotate does to the number 1. So we've got 0. Let's make a 2. So that'll be 2 twists. 1, 2. So here's clearly 2, and let's rotate. So now we have this unknown number. Let's do a display here. And great, I'm glad you remembered the cloud. Sometimes I'm forgetting. But look closely at this, and you'll see, let's say from your hand here, the yellow rope is sort of coming down in front of the green rope and going behind and back down, correct? So let's just take this and do a single twist to this unknown number, not the 2. And now continue the display. So what's changed? The yellow, instead of coming around the front, comes around the back.
But that's supposed to be positive.
Well, this is like the mirror image, isn't it? It's the, you know, from this to this is a reflection, right? So in other words, a rotate, we started with 2. We did a rotate command, and that got us to some unknown number u, okay? And now we notice that if I do a single twist to u, I get to the negative, I get to the mirror image of u, which should maybe be the negative of u. So in other words, I could write an equation. So it's sort of like u is the result of twist, twist. If I do a twist and a twist and a rotate, I'll write it that. I get to this unknown situation. But I do know that if I add 1 to it, namely do a twist to it, I appear to get to the negative of that same thing. Right? And now I can solve this one. Let's see, we subtract u from each side. So maybe, so in other words, let me write down some. So that's sort of interesting. Again, the notation you use can probably vary depending on the level of the kids in the class. I might just do something like this. I'll say the twist, we said take some number and it adds 1, right? If I take whatever the rope situation is and I twist, I add 1 to it. So that's a sort of a functional notation of what's going on here. And the question was, what is rotate of x equals? We don't know yet. But we did have some facts. We do know that if we rotate 1, we get -1. And it looks like if we rotate 2, we get -1/2. So maybe, move the question up to here, it's -1 over x. Maybe that's a reasonable thing for it. Okay? So, here's, okay, let's do one more reset. I promise this is the last one. Okay, next class. Let me show you one thing that, again, a lot of kids like. We're at 0. let's do rotate. So this is something or other. Another unknown number. We've used U. Let's call this one W. Okay? This unknown number. And do a twist.
Yeah.
So what happened?
Got itself.
We're back to this. Yeah, we're back to the identical thing, right? So W plus 1 is, it's still W. So I can solve that one too. So W was what happened when you rotate a 0. So if I rotate a 0, I get W, which I don't know what it is. But I do know that W plus 1 is W. So I can solve this one. 1 is W minus W, so 1 equals W times 0. No.
0.
Yeah, W times 1 minus 1, or W times 0. So W is 1 over 0. That's sort of problematic. But is it? I mean, now, does that sort of make some kind of, what is 1 over 0? I mean, it's undefined, and that's the correct answer in some sense. But we may not be using the usual arithmetic of the fractions. I mean, there aren't any real numbers which, when you add 1 to them, stay the same, right? Can you think of any sort of a thing that might? Yeah, so what if it is infinite? If you add 1, it'll still be infinite, right? So that would, if we sort of think of W as being infinite, and you add 1 to it, well, that's fine. Or does that fit in with this in some sense? I mean, if X is really tiny, this is going to be some huge negative number, right? So if X is 0, maybe it's like negative. Would negative infinity also work? If you add 1 to negative infinity, is it still negative infinity in some sense? You know, if you owe an infinite amount of money, and then you repay $1, how much do you owe? Well, you still owe an infinite amount of money, right? Or if you have an infinite amount of money and somebody gives you $1, you still have an infinite amount. So you could think of W as being either positive infinity or negative infinity. It doesn't really matter. It's some new thing that's not a regular number. But since we're not going to have to use all the rules of arithmetic in this thing, I mean, all we need to do is be able to add. We have to know how to add 1 to infinity, because the only operation we have is adding 1 and negative reciprocal. And so we just say, look, if you've got infinity and you add 1, we'll call it infinity. We'll just say that leaves you infinity. So that'll be a fine rule. And the other rule we have to know how to do is how to rotate infinity. And so what would a rotate of infinity? Here we are at infinity. Rotate. And what does a rotate of infinity do? Back to 0. And that's sort of like 1 over infinity, which would be, and if you put an incredibly large denominator, you're going to get close to 0. So it sort of makes sense. So if those are the operations we have, x plus, adding 1 to whatever the situation is, or taking the negative reciprocal, and these make perfect sense for every rational number, correct? You can certainly do that with every normal rational number except for 0. And then we say, okay, but if we have 0 and we rotate it, we'll say, that makes me a new number that I'm going to stick into the system. Just one more thing, and I'll call it infinity just for convenience. And now I have to tell what all the rules for infinity are, but there are not too many rules. If I add 1 to infinity, I will continue to call it infinity, and if I put infinity in the denominator here, I'll say that just brings me back to 0. And that should be fine. And we can see with the ropes that it does behave exactly that way. If you've got infinity and you twist it, it remains unchanged. And if you've got infinity and you rotate it, you're clearly back to 0. So, and those are the only things that have to happen. So for a sort of again, this is a more advanced kind of a mathematical thing that you can leave out the infinity stuff for the less mature kids. But it's sort of nice in the sense that, in mathematics, you're not forced to use the same number system every time. If you can come up with a system that fits your data and makes sense with all the operations and so forth, that's fine. It's just don't try and stick infinity into the usual fractions, because then you find, well, what's infinity minus infinity? All kinds of things just don't really work out all that well for you. But here, it's so constrained with only two operations that we can put the infinity in and say, our new system is the rational numbers plus this new object that I will temporarily call infinity that behaves according to these rules because it only has to work in these two situations, and we'll be fine. Okay, so let's maybe try and find some more evidence about this negative 1 over x. All we have is two data points here. 1 goes to negative 1, and 2 seems to go to negative 1/2, and we don't even know for sure that it's negative 1/2, right? So let's make a negative 1, what we think is a negative 1/2, and see if we can do it. So let's do two twists. There's a 1 more twist is 2. Do a rotate. We're probably at negative 1/2. How could we decide that, see if the negative 1/2 assignment to this makes sense? If we could somehow drive it to 0? Okay, let's do a twist. Okay, so this is positive 1/2, okay? Do a rotate, that should be negative. Negative. Right, so this, we thought we were at negative, we thought the value we had was negative 1/2. We did a twist just now, so if our theory is correct, and the twist always adds 1, we're definitely at plus 1/2 here. If we do a rotate to plus 1/2, we should now be at the negative reciprocal of plus 1/2, which is negative 2. So, in other words, 2 twists ought to bring it to 0. So let's try it. 1 twist, 2 twists. So it certainly continues to behave like 1/2, right? Display? You can still display. Okay, let's just try one more, just to convince ourselves. What's the next obvious one to try? 3. So let's make a 3. So 1, 2, 3, and now do a rotate. And this, if our theory is correct, should be negative 1/3. So how can we test that? We'd like to sort of grind it down to 0, maybe. You know, we know the 0 situation, so if we can do things that mathematically get us to 0, that fit with the negative 1/3, that'd be interesting. We're trying to get to 0. That's back where you started, right? So the only other, since rotate's not an option, the only hope of making any progress is a twist. Right. The nice thing about this system is there's only 2 ways to go at any stage, right? So it's a good twist. So this should be 2/3. Now, if you do a twist, you're trying to get to 0, right? You're at 2/3. If you twist, you're going to be pushing yourself farther and farther from 0. Right. Do a rotate. Yeah. Oh, good. Okay. So do a rotate. So we're now at negative 3/2. Okay. 2 twists. That's negative 1/2. This is positive 1/2. Actually, this is beginning to look familiar, isn't it?
And then we'll twist.
Do a rotate. Now you should be at negative 2. Now a negative 1 and 0. So that's sort of interesting. Okay.
We're going to have to practice this at home.
But the nice thing is there's not, that's it, those are the only rules. And so now it's, what I usually do is a more complicated one. We didn't get anything interesting here. So, and again, depending on the sophistication of the class, you can do something to, negative 341 473rds, or we can do like, negative 9/5 or something like that. So let's do sort of an intermediate-ish thing here. And let's just start with, like, say, 3 twists. So we're at 1, we're at 2, we're at 3. Let me go to the blackboard so that I don't lose track. I'm going to use a notation here. We start at 0, and I'm just going to use t cubed to indicate twist, 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 right? So the t cubed took from 0, added 3 to it, so we're now at 3, correct?
Yes.
And let's do a rotate. And so we're now at negative 1/3. Notice this, this negative 1 over x is nice too in that it satisfies do 2 rotates in a row and you're back to where you started. So there's never any point if you're trying to make progress to do 2 rotates in a row. Do multiple twists in a row can make sense, but you never, I mean 2 rotates just cancel each other out. So, basically anything interesting that you do with the rope can be done with some number of twists, a single rotate, some number of twists, a single rotate, etc. So, okay, let's say two more twists. Just 1, 2, so what does that do? It adds 2, so that's 6/3, so we're now at 5/3. Let's do a rotate now. Negative 3/5. And let's say, how about 4 twists? 1, 2, 3, 4, and that should add 20/5. So we're now at 17/5. Okay, display. So that's obviously 17. maybe
Exactly as I was expecting.
Yeah, it's just exactly what you thought. I just did this in the other, with the other group above, and I forget, I should have written it down. We came to some number that made a really pretty tangle. Maybe I should, write a computer program to draw pictures of them, of all the knots, and then we can select the prettiest one. Okay, anyway, so now we have 17/5. I mean, sort of, it's more interesting. It's not just a straight situation here. So let's see if our method actually will untangle it. So we're now at 17/5. Let's see if we can figure out how to get that thing down to 0 with a sequence. I mean, if we do a math sequence that gets us down to 0, it would be really nice if the tangle came out to 0
So
too,
we
right?
want to solve it before we do it?
No, let's solve it as we go. So we, and the nice thing is, there's always only two choices from whatever number you've got. Okay, and what's the obvious, so basically, from here, you could do either a twist or a rotate. And which one makes sense? Why?
Because you can only add. No, I don't want to.
Right, so if you add, if t will make bigger, you're already above 0. If you add, it's just going to make life worse, right? So since you're above 0, it probably makes sense to do a rotate. And it never makes sense to do 2, so let's do 1 rotate. And so we will now be at 5/17. Okay, now what? Obviously we've got to do twists, but how many? Let's just do 1 for a start. Yeah, do 1, and what is that going to do? It's going to add 17/17. So a single twist will take you to 12/17, correct? Okay, now another twist doesn't make sense because that'll push us farther from 0. So a rotate probably makes sense here. And we're now at negative 17/12, right? Now what? Yeah, you can sort of look ahead in the class. You can do it a step. You can think of this as, we do 1 and we're still negative. So I sort of want to keep doing twists until I either hit 0, in which case it's untangled, or until I flip over to positive. But once I'm positive, I don't want to keep twisting because that'll push me farther from 0. So, but if you're a little more advanced, you can look ahead and say, it's going to take 2 twists to get us past 17. That'll be 24. That'll be great. So 2 twists, that makes sense here. T squared. That'll add 24 to this. 24/12. So that'll be 7/12. Okay. And I'm just going to copy the 7/12 back here. Okay. Now what? Since we're positive, a rotate makes sense. Okay. Now what? Oh, and that. So we're now at negative 12/7.
Display.
Oh, display. Yeah. Sure.
How is it when we're
Well, that's a little simpler, maybe. I don't know.
That's how to get pressed them.
Okay, so we're at negative 12/7. How many? 2 twists. So that'll be 2/7, right? That adds 14/12. Rotate. Good. And that would be what? Negative 7/2. So we're going to need like 4 twists, right? 1, 2, 3. Oh, it's looking good.
Do we do it?
4
You need
twists.
4. Oh,
Because that'll add 8 halves.
yes.
So that was t to the 4th. And that takes us to 1/2. And this actually sort of looks like a 1/2, right? So now what do we do? Rotate. -2. And then two twists ought to bring us to 0.
2.
Ta-da!
Oh my goodness.
Okay, so now this is what I usually like to do. Pick something that's you know. Oh, let's just stop and take a quick look at this. Can somebody again kind of level the class and so forth? You can actually try and construct a proof. Maybe not that the ropes will behave this way, but that the arithmetic will behave this way. If I continue to do this operation, can you prove that these mathematical t and r functions will grind an arbitrary fraction down to 0? What's the algorithm we were using? Basically, we look at the number
If
and
it was positive, rotate to make negative,
and if it's negative,
add until you make positive.
yeah, it's basically simple. You twist if it's negative and you rotate if it's positive, right? So, will that get you guaranteed down to 0? And we have a lot of evidence here. Ignore the top one. We were generating the bad. We were generating our thing. But look underneath this line, and sort of look at what's going on here. Look at the pattern of the numbers. And they jump around a little bit, but they tend to get smaller. So that's good. You sort of want them to get smaller.
We're kind of like this oscillating state conversion group.
In fact, maybe this might actually have been a better way to do it. Is, you know, instead of doing t squared, maybe I should have done t and then t. Right. And so, in other words, it would be -17 twelfths, -5/12, and then 7/12. And then this would be 4 t's, right? It would be -7 halves, -5 halves, -3 halves, -1 half, plus 1 half, and so forth. And so, if you've got a positive number and you flip it over, what happens to the denominators? The numerators sort of jump around a little bit. Numerators, 5. The denominators are strictly decreased. I mean, not strictly. They're monotonically decreasing, right? They either stay the same or they get smaller. Well, except for the first one. Yeah, that's interesting too. But why are they decreasing? What's our operation here? I'm sort of like adding. Let's say we're in the 17th situation, a negative something or other 17ths. I keep adding 17 17ths, 17 17ths until what? Until it jumps over 0. It can't be over 17 because that would mean I took a step larger than 1. Right? I mean, the only reason I would add 1 to it is because I was definitely below 0, right? I got some numerator, some negative number of 17ths, and I keep stepping up and stepping up and stepping up. If I hit 0, great, I'm done. If I don't hit 0, when do I go positive? I had to be between -1 17th and -16 17ths, right? Those are the only things that would have allowed me to jump across. But I can never jump more than 17. I can never get to 18 17ths or 19 17ths. So when I jump across, I know that the numerator, whatever it is going to be smaller than 17, correct? And so what does that mean? And what do we do as soon as we got a positive number? We rotate, and that just basically turns it over and flips the sign. So you keep cranking the numerator down, or up, in this case, up towards 0 if it's negative, and then it finally jumps across, and the instant it jumps across, you yank it back in the denominator, and you know that that's reduced the denominator. Right? Now, no matter what number I had up here, even if this is -143, I don't know what it was to get there, but I mean, just keep adding 12, and then finally, I'll jump across. I know I've got a number between 1 and 11 when I step across the boundary. And so then when I turned, and it turned out, what was it? I got 7, right? A 7/12 when we step across the boundary. So flip that over. Now I know I've got 7s. And so I know when that steps over, it'll be a number between 1 and 6, and so forth. And so eventually, what's got to happen, we're going to get a denominator of 1, and then with a negative thing, so a negative number with a denominator of 1 then twists we know will grind that straight to 0. So does this sort of make sense? A proof that at least, it doesn't prove that the ropes do what you think, but it definitely proves that if we take an arbitrary fraction, positive or negative, and we use the rule that if it's negative, we invert it and flip the sign. If it's if it's negative, we add 1. If it's positive, we invert it and flip the sign. And no matter what fraction you start with, we sort of have constructed here a proof that by doing that, applying that algorithm enough times, you've got to get back to 0. Okay? So that's sort of nice. So if this works, and I'll tell you it does, for any of these knots, then we now have a guaranteed way to get from any, if we tangle this up in some horrible way, we know we can untangle it. And sort of, I think this is sort of cool because we're not allowed to do untwists, right? You can only twist it up and rotate it. It turns out with the correct sequence of twists and rotates, you can untangle any kind of a nightmare. So I wanted to, let me see what time it is. I wanted to make one slightly nightmarish thing, just to prove that. So let's see. I'll have plenty of data. In a second. Let's get it back to 0. Oh, we are at 0. And this time, to prove that it's not me who's making up these numbers to lead to very specific fractions, I'm going to let the audience tell me the number of, but it's going to obviously be to generate our number, we're going to have some number of twists and a rotate, some number of twists and a single rotate. And it turns out if you choose a large twist, like you say, do 20 twists in a row, it turns out in the untangling process it'll be a pretty boring, grinding thing. So I'm going to restrict the choices that the audience makes to be 5 or fewer twists in a row, okay? But other than, and trust me, it would work with larger ones, except that you might get bored out of your mind as we try and untangle. Okay, so we're at 0, and so from the audience, how many twists should we do? Between 1 and 5, or yeah, 2? 2. There's a 2. So we're now at a 2, and so then we'll do a rotate. -1. Okay. New number. 4. Okay. 1, 2, 3. Check my arithmetic too. So t to the 4th added 8 halves, so we're at 7 halves. Okay, rotate. -2 seconds. Okay. Another number.
3.
3. T cubed. 3. That adds 21 sevenths. So we're now at 19 sevenths. Sure, that would get you back to.
Well, I thought 2 rotates gets us back to the bottom.
So 3 rotates is the same as a single rotate.
Oh,
right?
Alright.
So let's do a. Did we do the rotate yet? No. Okay, do a
But
rotate.
3 would be more fun.
17 would
Why
be. So we're now at -7/19.
That's how much you wear on those kids in the classroom.
Yeah, for the ADHD or what. 1,000,001. Okay, so we're now at
Bounce up and down,
-7/19. How many now?
Somebody say the
What?
One twist.
Okay.
1 twist, okay. So that does us what? We're now at 12/19. A rotate. -19/12. 1, 2, whatever.
It's interesting, it's going to
Five
be less.
Yeah, we're getting smaller denominators here. Let's do more than 2 twists. Let's do like 4 twists. That was 2 you did, right? So do 4. I want to get 3, 4. So that adds 48 twelfths. So what are we now? 29 twelfths, right? Yeah, I want to get a decent sized denominator. Let's do a rotate here. And so we're now at -12/29. Okay, and I get the last choice. 5 rotates. I mean 5 twists. 1, 2, 3. That'll be a good horrible number. 4, 5. Okay, can somebody help me here?
Wow.
This is 145, 133, 29, right? Okay, so this display. Okay, and everybody sees that's obviously
Yay!
obviously
Well done.
obviously 133, 29, right? So, and the way we can prove that, of course, will be to apply our operations and get it back to 0. But just to make things interesting, excuse me, it's really not all that interesting if you can see what's going on. So what I'm going to do, what can possibly go wrong?
Getting tied in a knot.
Oh yeah, it's really gross right out. So interesting. We want to make sure that the knot is completely tangled up in this thing.
Good. Now, abracadabra.
We'll make absolutely sure it doesn't go away.
No, T5 is the last one. The one before that is a T1.
Clearly you've done this before.
Well, before the rotate goal, and blah, blah, T4.
Okay, so there. So we're now obviously at what this is
Display.
display.
Oh, there we go.
Okay, so there was our production of 133/29. This is one of the largest ones I've ever done. So rotate. So we're now at -29 over 133. One twist. Set at 104, 133, right? Rotate. -133 over 104. How many twists are we going to need? 2 twists, okay. 1, 2. Okay, that adds 208. It's 208 minus 133, right? 575. So this will be plus 75, 104. It's also sometimes a good idea in a class to have a couple of kids doing arithmetic on. So and then the class doing them, and so everybody can check. And they, if you get different numbers, then maybe you should do the calculations. And so I'm counting on some help here because I'm trying to think about other things. Okay, so we're at 75, 104. It's going to rotate. We'll get to -104 75ths. We did the rotate?
Yes.
Okay, so it looks like two twists. 1, 2. That adds 150. So that'll be at 46 75ths. I'm going to rotate. -75, 46. It looks like, what, 2 more? 2 twists. That'll add, what, 92. What? 92 minus 75 looks like 17. 1746. Rotate. -46 17ths. Looks like 3 is 51. 3 17ths is 51. T2. So 51 minus 46 is 5. 5 17ths. Okay, so we're 5 17ths. Rotate.
Display. Let's see what it looks like.
17 fifths. Display. Okay. Yeah, but you didn't clap. Thank you. Okay. Okay. It looks like 4. We'll add 20.
Yes.
1, 2, 3, 4. So that added 20/5, so we're now at 3/5. Okay, rotate. -5/3. Two twists. That would be, that adds 6/3, so we're 1/3. Oh, cool. Rotate. -3. 3 twists.
1, 2,
3. Display.
There's
Wow.
the picture.
There we go.
Wait.
Oh. Hold it.
Perfect.
So that proves it. So, yeah, it's not really totally obvious that this is untangled. We have some evidence. Luckily, the 2 yellows are on one side. I mean, if it is untangled, it would be terrible if there were yellows going across this way, right? So that's at least one good thing about this. But maybe you should use your, depending.
Add comic value.
Yeah, whatever it is. As long as there's enough violence to the bags, the kids will usually like
Go on,
it.
America's
So,
Got Talent.
yeah.
Uh-oh. No, they're just stuck inside each other.
Yeah, it's hopeless.
Never gonna work.
Well,
All never.
this is the first time I've ever screwed up.
Oh, right here.
I always get really worried at the end of this because it always looks like it's not going to happen. So I pay particular attention to the arithmetic while I'm doing it because it would be really anticlimactic to have a tangle at the end. Okay, well, thank you. How are we doing here? Okay. Okay, I've got time. I guess, I mean, there are other things you could do with the kids in the rope, but there's a lot of actual interesting mathematics that's going on here too. As opposed to what happened in another class, I'm not going to make the mistake of instantly erasing this, because there's some interesting information here. And that is, look at every fraction on the board here, and there are none of them that can be reduced. None of them are like 2 fourths or 4 eighths. Every one is in lowest terms, right? So that's sort of interesting. How many people here have heard of the Euclidean algorithm? For, what does it do?
For division, reducing division of dozen numbers.
Yeah, for finding the common denominator. If you want to find the common denominator of 2 numbers, it's what it's used for. And so, let me tell you the answer here, and then we'll see why it sort of applies. What we're sort of doing, let's say when we started with our 133/29s, and I'm telling, and I told you that this is a fraction that can't be reduced. It's in the lowest. There are no. What we're effectively doing here with these calculations is finding the common denominator between 133 and 29. And since it's reduced to lowest terms, that'll be 1, which is a really nice denominator to have down here because that'll let you dry to 0. Okay? And, okay, let me, okay, I've got an example here. Let me sort of show you how the Euclidean algorithm works. So the goal is we have a couple of numbers. Like let's say we have this, you ran into this fraction. Okay? And you say, well, that can be reduced. I mean, probably what I'd do is I'd say, oh, I can see that there's a factor of 4 in each one, and I'd reduce it down like that. But it might be that these were numbers that have very large prime numbers. And I mean, for the ones that come up in practice in elementary school, you can usually just do it by see and study. Okay, but if you have one with ugly, large primes and numerators and denominators, it might not be so easy. But what the Euclidean algorithm lets you do is it's a completely mechanical way of finding the common denominator, to find the largest. It would be great if some oracle just told you the largest number that goes into both 700 and 4004 is x, and then you could just divide that x into 700 and that x into 4004, and you would have the fraction reduced to the lowest terms, right? And so what the Euclidean algorithm does is it's a way to find out what that number is, what the largest number is. I'd like to say 700 is x times something and x times something else, and so the answer is something over something else. Okay, so here's the idea. You can say, well, if I'm really lucky, 4004 is an exact multiple of 700. Wouldn't that be great? Because then 700 would be the answer. So divide 700 into 4004, and, well, it doesn't work out. It goes in 5 times would be 3500, 6 times would be 4200. So it's really 700 times 5, right, plus a remainder. Okay, and what's the remainder going to be? 3500, it would be 504, right? This is, so 700 is not the greatest common divisor. 700 doesn't work. But if there's some number that does work, it has to divide exactly into 4004. And it has to divide exactly into 700, right? So it also must divide exactly into 504. Right? Because if it goes into here and it goes into here, it also has to go into here. So whatever your largest common denominator is, it has to go into both 700 and 504. So, in other words, if I can find the greatest common divisor of 700 and 504, that's the same as the greatest common divisor of 700 and 4004. So I could just start over again. I could say, well, maybe I'm lucky and 504 is the answer. Well, no. It goes in once, and what do we get, 196? Yeah, you can see this. Your arithmetic does get some practice here. I mean, maybe more for me than for the kids. But you say, okay, but now we can repeat the exact same argument. I'm trying to find the largest number that goes into 700 and 504 because I know that'll be the answer here. And whatever goes into here and goes into here has got to go into 196. So I can find the common denominator of 504 and 196. I'll be in business. So maybe I'm lucky, and 504 is 196 is an exact multiple of 196, but it's not. Yeah, it goes in twice over here. Now, arithmetic gets even harder. What is that? 392, right? 392. So that's 392.
202. No,
112.
112.
Okay. Okay. So the same argument again. Whatever is the greatest common divisor between 112 and 196 will be the answer. So 196 equals 112 times 1, right? Plus 84. So maybe 112 and 112 equals 84 times 1 plus 28. Right? 84 equals 28 times 3. Wait. Yeah. Plus 0. So 28 went in exactly. So 28 is the greatest common divisor of 84 and 112. And the greatest common divisor of 84 and 112 is the same as the greatest common divisor of 112 and 196. And the greatest common divisor of 112 and 196 is the same as the greatest common divisor of 196 and 504, and up and up and up. And so now I know 28 goes into both 4004 and 700, and 28 is the largest possible number. Now, let me tell you, this seems to be totally unrelated to this, but in fact it's almost exactly the same with one weird change, and that's the following. Imagine that we don't know how to multiply. All I can do is add and subtract. And I'm saying, how many times does 700 go into 4004? If you can't divide, what could you do? I could just keep subtracting, right? I can subtract 700 and 700 and 700, and then suddenly, finally, what's going to happen? It's going to go negative, right? When you say, oh, that's one too many, you know, after you subtracted your 6 700s and it went negative, you could say, oh, 6 was too many, 5 is fine. And so after I subtracted 5 of them, I was at 504. And then the same thing here, we get a 1 and so forth. What were we doing here when we're doing twists? We're basically adding 133 133rds until what? We flip over the sign. That one's pretty easy, but with this negative 75 46, for example, right? We add 46 46, it's still negative. We add 46 46, oh, I'm okay. I've now flipped over. It's just, it's sort of adding to a negative rather than subtracting from a positive. But we're doing the same sort of thing here. I don't know if this is making sense to you. But yes, question?
I don't want to belabor it, but two quick questions. What's it called again, this thing?
This is called the Euclidean algorithm.
And
It finds the greatest common divisor,
Okay.
GCD, of two numbers.
can you say one more time the explanation
Sure.
for why it is that
Right.
700 and 504?
Yes, okay. I want to find the biggest number that goes into 4004 and into 700, right? And you might be lucky, it might be as large as 700. So, I mean, you know, if I had had 1,000 and 250 as kind of say, what's the greatest common divisor? You'd say, well, the biggest it could be is 250. Oh, 250 times 4, it's 250, right? So you say, maybe it's 700, you know, maybe we're lucky. So you say, well, I'll try and divide 700 in, and I can do that either by this repeated subtraction if we can't do division. But we just divide it and say it goes in 5 times, but darn, it didn't go in exactly. It went in 5 times, but there was some junk left over. And so you say, well, whatever is the largest number that goes into here and here, if x divides into here and x divides into here, and this is an equality, then it better divide into here, right? And so whatever number works for 4004 and 700 had better also be the largest number that goes into 700 and 504. So I can say, oh, I've now got a simpler problem with smaller numbers, 700 and 504. And so I can just say, well, let's start with 700 and 504 and do exactly the same thing. And the exact same thing says, maybe I'm lucky, maybe it's 504. You divide it in, oh no, I'm unlucky, I got 196 left over. But after a certain point, it does magically come out to 0. Now, suppose that they don't have anything larger than 1. What will happen is you'll grind all the way down and you'll get a 1. And you say, oh, 1's the greatest common. And that basically means that it was already reduced to lowest terms. But this is, if it's not, it will pop out at some point where you get some number, which is that did work. 28 happened to be we got to this stage. Whatever the greatest common divisor of 1, 12, and 84 is, also has to be a 28. Well, maybe we're lucky and 28 will work, and oh, it did. So 28 was the answer, and you go back up. So whenever you get a remainder of 0, that means you hit the end. Oh, I should say one more thing. I think Brandy will probably put it on the website or something like that. But I have a very complete notes for how to do this in class, a complete description of all of it, and a complete description for all kinds of different directions you can go. This greatest common divisor thing is just one of them. So let me give you the address of my website that has the complete handout. It's sort of a teacher's guide to how to do this in class. And it's at www.geometer, G-E-O-M-E-T, so person who does geometry.org /math circles, M-A-T-H-C-L-I-C-T-S. And this particular one,
So everything into that directory is yours.
yes, tangle.pdf. And if you don't type the tangle.pdf, you get an index of all the handouts I've ever done for any math circle ever that I wrote up. There's, I don't know, there's probably about 50 of them in there. And if you don't do math circles, you can find how I waste my time in the non-mathematical work. Yeah, geometer.org is my website. So anyway, that's for letting that document go in a whole bunch of different directions. We're probably going to have time to only look at a couple of them. So there are a couple of things where this, as I said, it's very closely related to the Euclidean algorithm, but it turns out not to work exactly like this. And let me say, what if I had said 4004 is 700 times 6? What would have happened? We would have gotten a negative number here. But it would still have been a negative number smaller than 700, right? Because this is just like stepping beyond. And if you ignore, I mean, if I'm trying to find greatest common denominator, I don't mind about positives and negatives. You know, if I had a negative number here, I could find the greatest common denominator between a negative number and this, and it'll be the same thing as with the positive number. It might go faster in the negative direction. And in fact, that's exactly what we're doing here in this tangle thing, is we're actually, if we had gotten to the fraction 700, well, we wouldn't have, because we would never get to one that was in a not reduced in lowest terms. But if we had somehow done the fraction, if we had applied this algorithm to 4004 and 700, it would have done the equivalent of having a 700 times 6 minus something. It's sort of like, you know, if you can't do division and you do division by subtraction, and let's say you can't even, the only thing you notice is when you go negative. You know, you could just say, I'm going to just keep subtracting 700 from 4004. Yeah, went in once, went in twice, went in 3, 4, 5. You subtracted the 6th time, oops, I went negative. Okay, I'm beyond, you know, so that, and the nice thing is you don't even have to back up one. You can just use the 700 times 6, and if you're willing to work with negative numbers, that would work fine. And in fact, that's exactly what you're doing here. It's sort of like to think of it as you know, you can back up a car to your braking glass, and, oh, that's too far. So anyway, this is the Euclidean algorithm and how it applies exactly. So that's a fairly sophisticated thing. Here's an easier question that you could ask, and that is, we know how to get to, if I give you a tangle, you know, if the class or whoever has tangled it up and you got some wacky number, 73 over 42, we now know how to get it back down to 0 by applying twists with our algorithm, which is basically if it's negative, you add what you twist, if it's positive, you rotate, right? But the question, the other question you ask is, could I get to every possible number? In other words, is there some way you could start from the 0 row, the 0 configuration, and get to negative 42/73? We know we can get from negative 42/73 down to 0, but can I get from 0 to every possible positive and negative fraction? Well, I would like to have some sort of an algorithm that would, you know, guarantee that I'll get there. Right? I mean, that would, we would be much, I mean, you can say that it seems that you probably can, right?
Well, you can just reverse what we did.
Well, you can't, because you can't reverse a twist.
But I mean,
You need-
mathematically, you can reverse it and then say, okay, that's how you do it.
Yeah, how do you
Solve it backwards.
mathematically
Solve
reverse
it
a twist? Yeah, okay, that's a really good idea.
Shall we try a particular example?
Oh, okay. Well, let's look at, I don't want to start with these huge numbers like this that take a long time, but let me just, let's take a fairly small thing that we can grind down to 0, like 7/5 or something like that, right?
And so can you grind any number down
Well,
to 0 this way?
oh, yeah, we know we can grind any number down because we know the algorithm basically kept, you know, if we're positive, we flip it over, right? We get negative 5/7. And now I'm going to keep adding 7s until the numerator goes positive and it can't be bigger than 7,
Okay.
right? And then we'll flip it.
But I
So
don't know what the knot looks like.
we don't know what the knot looks like. But I just want to write this down for a second and see what happens. I want to start with something that's not a huge example like this, but I want to have a complete example to grind down, okay? So then we would do a single twist, and that would be now 2/7, right? And now we would do a rotate, which would be -7 halves, right? And now we would do 4 twists, and that will be 1 half. Then a rotate would take us to -2, and 2 twists to 0, right? And as I said earlier today, if you were allowed, we know rotate undoes itself. Rotate of a rotate basically undoes the operation. So if we were allowed to use this untwist operation, which we normally aren't able to do, if you could do an untwist, is it obvious how to get to 7/5? How would you do that? Start with 0, do 2 untwists, that would get you to -2. Do a rotate, that would get you to 1 half. Do 4 untwists, and that would take you to this. Do you see that? So in other words, we're not allowed to do untwists. But if we could, it's really obvious. In other words, if I gave you a rope and I said, make me a 7/5, you know, without worrying about using legal operations, you could certainly do it. You'd start with 0. You take your number that you're interested in, you grind it down to 0, and you know you can do that. And then you say, now all I have to do is reverse these operations. You know, as I say, to undo something, you just do the opposite operation in the opposite order. So you'd start with a 0, you'd do 2 untwists, and an untwist subtracts 1, so that would get you to -2. An unrotate is the same as a rotate, so that would get you to 1 half. Then we do 4 untwists and get to -7 halves and so forth. So we could easily work our way up the chain. Okay?
So you said rotate and opposite rotate is the same thing?
Yeah,
Is that what you
because
said?
remember, rotate of x. If you rotate twice in a row, it turns it first into -1 over x, and then it turns into -1 over -1 over x, which is back to x. So 2 rotates in a row get you where you started. So that means rotate,
Rotates in a row.
2 rotates in a row, right. So in other words, if you've done a rotate and you want to undo it, the unrotate is the same as, rotate is the same as unrotate.
How
Ro-
would you do the untwist?
Well, that's the problem, we can't. I mean, using our,
The what?
and I'm saying if untwists were legal, it's really obvious how to get to any number. You say you start with a number, you figure out how to get there with your standard twists and rotates, and then I could take a 0, and that's easy. I could do 2 untwists, that would get me to -2. And basically I just start with 0 and go the opposite way by doing the opposite operations each time, and I'll get to 7/5. Okay? But that wasn't the question I had. The question I had was, using only the standard operations, the twist and the rotate, could we figure out some way to get from 0 to 7/5? And so, do you have a comment?
I don't know, it's just a stab at it, but I was wondering if maybe you look at all those denominators, like the 2, the 7, and you think, okay, I'm gonna shoot for those denominators, so I'm gonna first do 2 positive twists, and then when I flip that over, I'll be able to do the 1 half, or some version of
Yeah.
that.
Okay, so you're saying, you know, let's just reverse them and see what happens. I mean, we don't have the untwists, right? But let's just do twists and see what happens. Well, what would happen if I started with 0 and I did twists instead of
You
untwists?
end up with the opposite sign.
Yeah, so 0, let me just, let me pretend that twist is, since I can't do an untwist, let's just do twists. So I'm going to start with 0, I'm going to do 2 twists. What does that give me to? 2. And now the next thing, since I'm undoing, the next thing I should do is a rotate. What does that get me to? Then it says I'm supposed to do 4 twists, so let's do 4 twists. What would that be? 7 halves. And now I'm supposed to do a rotate. Now what? I'm supposed to do a single twist, plus 5/7, and a single rotate, and then what? Oh, that's it. Okay.
So instead of starting with 2 twists, could you start with a rotate?
Well, let's look at this for a second. You see any relationship between these and the numbers? All I did is I started at 0 and I did the operations in the exact opposite order. And I don't expect to come out to the same answer. because twist adds one, and I really wanted to do untwist if I were trying to get to the, you know, to 7/5. But what did happen? We started at 0, here we start at 0. And the next step before is -2, here's +2. Positive a half, negative a half. -7/2 plus 7/2. 2 sevenths, -2 sevenths. -5 sevenths, 5 sevenths. And in every stage, what's the situation? I get the exact opposite numbers. In other words, if I have a sequence that grinds me down to 0, and I simply reverse the sequence starting from 0, where do I wind up with? At the opposite of where I started. So if I'd started with, my target, let's say, is to make a 7/5 in the knot. So I can say, oh, I can grind -7/5 down to 0. Ta-da. Then what? Then I say I take that sequence, whatever it was, and reverse it, and that will grind me to the negative of -7/5, which is the positive 7/5 that I wanted. Okay? So it's not a complete proof here, but it's not too hard to convince yourself that this will always yield exactly the opposite things. I mean, you know, a twist took us, you know, 2 steps in the positive direction, and that's what I want to do. I mean, instead of going to -2, I'm going to go 2 in the positive direction, so I'll go to +2. The rotate obviously does the, I mean, it just does the negative reciprocal each time. And so at every stage, it's pretty clear, I think, that whatever the number that was, you know, the thing was generated in the opposite direction here will be generated here, but with the opposite sign. And so here is a scheme to make any number. So if somebody says, I got my kids in the front of the room, they're only allowed to do twists and rotates, can you make me a the number 7/5? You can do it by saying, okay, I'm going to secretly first do the calculation of taking -7/5, and whatever steps those are, I'll grind that down to 0. And now I will simply read off the, in reverse order, the operations I did. And instead of grinding me to -7/5, it'll grind me to +7/5, which was the target I was looking for. So this is basically a sort of a proof that you can start from 0 and get to absolutely any fraction that you want. Okay, so that's an interesting thing. Let me see, I want to remind myself of a couple of 11 minutes. Just sort of step through here and see what else we got that could be covered here. So I get to 0, base common divisor, proof of the convergence. You could get to any possible tangle number. Oh, yeah, here's an interesting thing. You could basically list every possible tangle as, since they're just fractions. Imagine that you have the grid of, I can subtract it, erase anything, right? This is, it's all in this unit. When I have a fraction, you know, at any stage I've got some number over some other number, you know, plus or minus, I don't know. But basically, you could plot on the grid all of your fractions where I'll basically put the numerator here and the denominator here. Okay, so 1/2 would be 1 in the numerator direction. So this would represent the fraction 1/2, right? And the number 2 would be 2 over 1. So this would be the fraction 2. Okay? And so I could put a dot down on my grid to indicate every possible fraction you can get to. Make sense? Now, but we never had fractions like 2/4. They were always reduced to lowest terms. Where would 2/4 be? There's 2/4, which is one that we can't get to. But that's just exactly on this line, isn't it? And in fact, this line will have 3/6 on it, and 4/8, and so forth. So, if you think about it, every number, and in fact, -1, -2 is the same as 1/2, right? I mean, it's the same. This would also reduce to 1/2. In fact, every fraction that's equivalent to 1/2, if you plot it on your numerator-denominator grid, will lie, every point on this line, except for the origin itself, will lie on this line. Right? Now, what are the two operations we could do? We can add 1. So basically, okay, so my point is, every fraction is a line. And it goes through some lattice point, and we only use the nearest one to indicate the number. Every other one is sort of equivalent, and it doesn't really count. But if we add 1 to this, so this line here represents the tangle 1/2, right? Numerator's 1, denominator's 1/2. And so this line is the tangle. It stands for the number for the fraction 1/2. If we wanted to add 1 to 1/2, what do we? That should get us to 3/2, right? So how do you get to 3/2? How would you convert this line to the 3/2 line? Sort of go to the first point on the line, and it's over at 2, right? So I move 2 steps up, and so it's the line that goes here. So this will be the 3/2 line. So in other words, when you're doing your tangles, when you do a twist, you're basically taking the line that represented the previous twist and moving it to here. Now, the reason I bring this up is because this actually comes up. A lot of kids in algebra class who have been doing a lot of plotting with lines and stuff say, where have you seen this -1 over, x? The perpendicular line, right? What would be the line that's -2? It's the perpendicular to this line. Okay, so that's what's going on in some sense. You can think of this as, let's think about what does our algorithm look like when we're trying to grind numbers down. If we're positive, in other words, the line has actually got a positive slope, right? What did we do to it? We rotate, which does what? Takes the perpendicular line to it. So if we've got a positive number, our line now becomes like this. And now what do? We start cranking it up step by step by step until what? It steps across the boundary, and then as soon as it's across, what do? Flip it over to the perpendicular. And then step, 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 flip it over and so on. And then finally we'll get to the point where the line is like that, and then a single, or -3 or -4, something like that, in which case the line will step right back up to the horizontal line, which means we're done. So the reason I brought this up is kids often see the -1 over x and it pops into their head. That's the same as finding the perpendicular, well, they've seen m, where m is the slope of the line. -1 over m is the slope of the perpendicular line. And so in fact, you can keep track of what's going on, and you can think of it also in terms of just manipulating lines geometrically on the plane. So that's a sort of another idea. Yeah?
Do you ever have them just look at the ropes as well, and kind of for them to know, like, ropes that are coming across like that are horizontal, they represent like a horizontal slope, and ropes that are vertical like that are like a vertical slope, because that was the undefined one.
Yeah, well, yeah, it's not quite that simple. I mean, you've got these horrible tangles that represent the intermediate slopes. It's hard to see how any of the, it works great for those two
only
positions,
those, yeah, exactly.
just those positions. But it is sort of nice that to rotate it by 90 degrees does, I think that's just pure chance, that the rotate by 90 degrees, in fact, corresponds exactly to a rotation of your line by exactly 90 degrees. That is sort of a miraculous thing, isn't it? I think I'm probably about out of time. I've still got a couple minutes. So what was the other thing? Oh, I was interested, there's some stuff in here about the minimum half down to 0. Here's an interesting thing. I'll show you one more interesting thing. Let's see if I mess this up. I I'm gonna suppose we start with some kind of a tangle, and I don't know what it is, you know, in some mystery room it's been all tangled up, and I have no idea what number it is, all I know is it's some fraction. I'm just gonna call it x, okay? And what I'm gonna do to x is I'm gonna do a rotate, and a twist, and a rotate, and a twist, and a rotate, and a twist, just to see what happens. So what's gonna happen? X will go, x with a rotate, negative 1 over x, right? Now I'm supposed to do a twist to it. What do I get? You'll get what, x minus 1 over x, correct? I've added x over x. I'm going to assume that x is positive. Let's just assume positive for a second. Okay, then we do a rotate. What do we got now? Negative x over x minus 1. Now what do I do? Twist? What does that do? I add x minus 1 over x minus 1. That's negative 1 over x minus 1. Now I go rotate. What do I get? Negative reciprocal is x minus 1. Now a twist. X. So in other words, if you do that, those 6 operations, rotate, then twist, then rotate, then twist, then rotate, then twist, to anything, you get back to exactly what you had. Okay? In group theory, yeah. I mean, this is like one of the, what do you call it? One of the conditions on generators. Not a cycle, it's one of the generating conditions. You say, this thing is the identity, right? If you do this thing, the 6 operations, it's the same as doing absolutely nothing. In the same sense that R times R is doing exactly nothing. It turns out RT does exactly nothing. Okay, and it also turns out that TR does exactly nothing. Yeah?
I was just gonna say when we were trying to figure out how to undo, that's what I figured out, that RT was subtraction. That's subtraction.
Right, that's
so go to
subtraction.
x to x minus 1.
Right. So
that's
in
how
other
to
words,
subtract.
this
Right, yeah.
is the subtract one,
Right, yeah,
right?
yeah.
So in other words, we have in other words, now it won't be the fast, it'll be a pretty slow and unpleasant way, but it's a completely general way of getting there. So in other words, you say, how do I undo 5 twists? I do RT 5 times. Each one of these subtract, right, if we stop here, we got from x to x minus 1, right? RT is always subtracts 1 from what you have. So in other words, there is a way to undo a single twist, namely RT. So in other words, let's look at that. Suppose that I say, how can I undo, we started with the untangled rope. I did 3 twists, so we've got 3 half twists, and I now want to untangle it, and I don't care how painful and unpleasant it is. I don't want the fastest way, I just want a guaranteed way to do it. How can I undo the first twist? RT. How can I undo the next one? RT. Okay? So I can say, okay, I can undo this by doing RT, right?
Can you
Oh,
rid of
but
those?
doing 2 R's in a row is sort of pointless. So I could leave those out. I mean, that's just stupid to do those. And so really, I could undo t cubed with RT squared, RT. Okay? And let's say, it's sort of interesting, what if I had t to the 10th? It would just be this pattern over and over. You'd have a lot of RT squareds in here, right? If this were t to the 10th instead of t cubed, I would have 10 copies of RT. And so, but between every pair, there'd be 2 R's in a row, and that's stupid. You could just leave those out, and that'll bring 2 t's together, so you get t squared. And what you have is a sequence of a whole lot of 8 or 9 of the RT squared.
Or you can alternate using the TR, which is
Yeah, so there are various things you can do, but it turns out if you, I wrote some, when I first was trying to figure out what was going on, I wrote some computer programs to find the shortest paths down to zero from certain things to find out how efficient all this was and so forth and so on. And I was amazed at how often RT squared, RT squared, RT squared showed up in the patterns, and well, now I think I understand a little bit. So, anyway, there's a lot of material here, obviously, and for little tiny kids, you just, I mean, not little tiny kids, but kids that can do arithmetic on positive and negative fractions, you can just tell them, t adds 1, r takes it to -1 over x, and let's just practice with a few, and they miraculously untangle, and you keep the numerators and denominators less than 10 or 20, and there you go. For college kids, there's other stuff. Anyway, stuff everywhere. So that's pretty much it.